This is primitive roots and indices lecture number 7, and in this lecture we want to discuss about composite numbers having primitive roots. So to start with, I'll take an example. Let n is equal to 9, and we know for 9 2 is a primitive root of 9. And let's also recall here what is the definition of the primitive root. Primitive root is if it satisfies this sort of the congruences modulo n, and in this case I have considered n as 9, so this means 2 to the power phi of 9 should be congruent to 1 modulo 9, and this is the smallest highest power that makes this congruent to equal to 1. For any smaller power k, this is not congruent to 1 modulo 9, and hence I have considered this as the primitive root. So for more details you can watch my previous lectures. Okay, we'll move now forward. What is the most important result now here available for the composite numbers? The main result speaks about an integer n greater than 1 has a primitive root if and only if n is of this type and p is an odd prime. So this means this also does not cover all composite number but of certain particular type of this type. That means any other composite number which is not of this form will not have the primitive root. To prove the main result, we'll break down this into many smaller theorems or the lemmas. And in that context, our first result is, so theorem 1 speaks about for k greater than or equal to 3, the integer 2 to the power k has no primitive root. And we can see here by example, so suppose if we take k is equal to 3, then 2 to the power 3 becomes 8. 2 to the power 3, this is 8, and 8 has no primitive root. 8 has no primitive root. And also any integer of the form 2 to the power k is not covered in main result. So this means this type of the n has no primitive roots. Now we will prove this result by induction. And also by the definition of the primitive root, we know that the GCD of a and that n should be equal to 1. Here we want to search the primitive root for 2 to the power k. This means what is the value for n? N is 2 to the power k. And in this case we want to show that there is the order of a is h, and once I say the order of a is h, that means a raised to power h is congruent to 1 modulo 2 to the power k, and for some h strictly less than phi of 2 to the power k. So if such h exists, so this implies a is not a primitive root of 2 to the power k. And hence we'll say, because we have selected any journal A, we'll say that integer 2 to the power k has no primitive root. And also let us see what is phi to the power k. Phi to the power k is by formula 2 to the power k minus 2 to the power k minus 1. I can take 2 to the power k minus k common, and then I have 1 minus 1 by 2. This quantity is same as 2 to the power k into half. So this is 2 to the power k minus 1. So this means what we wanted is, we wanted a to the power phi of 2 to the power k should be congruent to 1 modulo n, 1 modulo 2 to the power k for primitive root, or we also wanted a to the power 2 times k minus 1. So I am just replacing phi 2 to the power k. This is congruent to 1 modulo 2 to the power k. Okay, this is what we desired. But what I'll take is, so now consider a 2 to the power k minus 2. I am just considering one less power. Consider this. We will show that 1 holds, So when we'll show that 1 holds, that ensure that the power that we have considered is less than what is desired. So this means order is 2 to the power k minus 2 and not 2 to the power k minus 1. And if it holds, this means a is not a primitive of 2 to the power k. And we are talking about any journal A whose GCD with n is equal to 1. So that will ensure that 2 to the power k has no primitive root. Okay, now this result I am proving by induction. We will prove 1 by induction. And also note here that once we apply induction, k is given as greater than or equal to 3 in the statement. So that least value I can choose for k is equal to 3. If k is equal to 3, then 1 implies I have a to the power 2 times k is 3. So this is 3 minus 2. This is same as a square. This is same as congruent to 1 modulo 2 to the power 3. Okay, so this implies my congruence is a square congruent to 1 modulo 8. So we are saying that this hold, and there are many numbers which are true for this. Take a is equal to 1. We wanted to select a number a whose GCD with 8 is equal to 1. So there are numbers a. If we take a is equal to 1, so we know 1 square is congruent to 1, as we say 1 square is congruent to 1. If we take a is equal to 3, then we know 3 square is congruent to 9, so it is congruent to 1. We can take a is equal to 5, so we know 5 square is 25, and that is congruent to 1. We may also take this as 7, so it is 7 square, that is 49. So 7 square is congruent to 1 modulo 8. So this hold. So this means for a smaller term, there is a quantity which is congruent to 1. So it holds for k is equal to 3. Now let us take the result is, so assume result is true for k. Okay, and we will prove. So this means once I say the result is true for k, so a to the power, so this means once I say the result is true for k, so this means a to the power 2 times k minus 2 is congruent to 1 modulo 2 to the power k holds. And now we want to prove for the next, to prove for k plus 1. This means what we want to show is a to the power 2 times k. If I replace k by k plus 1, so this quantity will become k minus 1. This is congruent to 1 modulo 2 to the power k plus 1. And we want to show that this congruence holds. Now let's start from the induction step. This is step number 2, induction step. So if I take from 2, which is the induction step, which is supposed to be true, a to the power 2 times k minus 2 is congruent to 1 modulo 2 to the power k. This is induction step. This implies 2 to the power k divides a to the power 2 times k minus 2 minus 1. Or I may say a to k minus 2 minus 1 is a multiple of 2 to the power k for some b belonging to integers. Or I may also consider this as a to the power 2 times k minus 2. This is equal to 1 plus b into 2 to the power k. Squaring both side, we get a to the power 2 times 2 to the power k minus 2 whole square. This is equal to 1 plus b into 2 to the power k whole square. Once we square this whole quantity, so we get a plus b whole square formula. So we have 1 plus 2 into b into 2 to the power k plus b into 2 to the power k whole square. And on the left hand side, because it is square and already there is a power of a, so the powers are going to multiply. So once the powers are going to multiply, so this means it is 2 to the power k minus 2 multiplied by this power 2, which means this is nothing but 2 to the power 1, and hence it becomes 2 to the power k minus 1. So on the left hand side I have 2 to the power k minus 1, and on the right hand side if I take 2 to the power k plus 1 common, so the first term leaves quantity b and the second term leaves 2 to the power k minus 1, because I require here 2k, and hence once you multiply the 2 to the power k plus 1 with this 2 to the power k minus 1, we get the same quantity. This quantity I can write further congruent to 1 modulo 2 to the power k plus 1, because it is a multiple of 2 to the power k plus 1. So this quantity is a multiple of this, and this is the remainder, so this is left here as 1. This implies that our induction step is completed, which we wanted to prove for k plus 1. This is what we wanted to prove. This is equation number 3, and hence 3 hold. And hence 3 holds. So this means this statement is the general statement that we have proved, and it is true for any a. So a to the power 2 k minus 2 is congruent to 1 modulo 2 to the power k. Implies that a has order 2 to the power k minus 2 modulo 2 to the power k. So the order is less than, and this order is strictly less than phi of 2 to the power k. So this means 2 to the power k has no primitive root. Now in theorem 2 we want to prove that if GCD of m and n is equal to 1 and m and n both are strictly greater than 2, then integer mn has no primitive roots. So again, when we have taken m and n to be any number which are strictly greater than 2, they are composite number, and again probably they are the product of the composite number that we want to consider. So let us start here. Consider integer a for which GCD of a and mn is equal to 1. Okay. For the primitive root, what we wanted to show is, for primitive roots, what we want to show is, we want to show a to the power phi of mn should be congruent to 1 modulo mn. Okay. And not for the smaller power. But what we'll prove in the theorem is that there is a smaller power that makes a to that power h is congruent to 1 modulo mn, and h comes out to be smaller than phi of mn. So to show mn has no primitive root, we will show a to the power h is congruent to 1 modulo mn and h is strictly less than phi of mn. This is what we will show. Okay. Once we can prove this, we are done with our result, and it ensures that mn has no primitive root. Now to do that, let me to start again from the given condition. What is given to us is, we have been given is the GCD of a and mn is equal to 1. I have to consider d of GCD of a and mn is equal to 1. Why? This is a given condition whenever we talk about the primitive root. So I have considered a number a for which the GCD of m and n is equal to 1. And this implies, so there is a result in this divisibility, that GCD of a and n is equal to 1 and GCD of a and n is equal to 1. If this hold, then the other side will hold, and if this hold, then this side will automatically hold. And I'm just going to label this. So put h as the least common multiple of phi m and phi n quantity, and let me to take d as the GCD of phi m and phi n quantity. And we know the result, as we know, GCD of two numbers phi m into phi n and least common multiple of the two numbers phi m and to phi n, if we take the product of these two, this is the product of the numbers phi m into phi n. So this is the result that I am going to use. Once I use this result, so this itself means h, which is phi m into phi n divided by d. So I am going to take the multiple. This quantity GCD I have considered as d, this quantity I have taken it as h, and this is the product of number. So simply divide this d on the other side, we get the expression of h as this. This quantity is definitely less than or equal to phi of mn by 2. Why phi of mn? Because we have already considered numerators are equal, as the GCD of mn is 1. GCD of m and n is equal to 1. So, and phi is a multiplicative function, so I can write phi m as same as phi m into phi n. But my divisor, the GCD, because both quantity m is strictly greater than 2, n is strictly greater than 2. So this means this divisor's least possibility is 2. Okay. And once I replace this quantity by 1 by 2, this quantity becomes the larger than the left hand side. And now I'm going to use my Euler's theorem. And now, by Euler's theorem, we know a to the power phi of m is always congruent to 1 modulo m. This holds always true once we know that GCD of a and m is 1. This is true. And raising both sides to power this, we get a to the power phi of m whole to the power phi n by d. This is congruent to 1 to the power phi n by d, which is same as congruent to 1, because 1 to the power any quantity is this modulo m. What we have in the left hand side, we have a to the power phi m into phi n divided by d. This is same as a to the power h. This is same as a to the power h, so I am replacing, and on the right hand side I got 1 modulo m. And hence this implies that a to the power h is congruent to 1 modulo m. And we know that this power h, which is phi m into phi n by d, this is less than phi of mn divided by 2. And this is less than phi of mn by 2, and which is strictly further less than phi of m of n. This is the power that we required it for the primitive root. Similarly, we have a to the power phi n is congruent to 1 modulo n by Euler's theorem. And again, raising both sides by phi m by n, we will have a to the power h is congruent to 1 modulo n. Now, once we have incongruences with respect to modulo m and another we have with respect to n, from 1 and 2, we get a to the power h is congruent to 1 modulo mn, because the GCD of mn was 1. And this proves our result because h is, so this implies a is not a primitive root of mn, because h is less than phi of mn, and this is what we desired for primitive root. And now theorem 1 and 2 gives a very nice corollary from here. The integer n fails to have a primitive root if either n is divisible by 2 odd prime. So this means if there are two different odd primes, p1, p2, that divide n, and we know that the GCD of p1 and p2 is equal to 1. This means p1 divides n and p2 divides n. So the second theorem falls in picture, and we'll have that n will not have a primitive roots. And the second case says that n is of the form 2 to the power m into p to the power k. Again, because p is odd, so the GCD of 2 and p is equal to 1, and we are taking the product of such prime. So theorem 2 again will fall in picture, and hence it will not have a primitive root. Now let me to take few example for the first case. So example for the case A. Let me take the smallest odd primes 3 and 5. GCD of 3 and 5 is equal to 1. So this means when I take the product of 3 and 5, this is the number n is equal to 15. 15 have no primitive root, and we can see this from the table that 15 have no primitive root. Okay. Whenever we will have a number n that is divisible by the product of two primes, okay, those two primes that we are considering, n will not have the primitive root. Second it says 2 to the power m into p to the power k, and m is greater than or equal to 2. That means least value I can take 2. Suppose it is 2 to the power 2, and then we have some odd prime. So this is 4 into p to the power k. And suppose if I take this p quantities also as p has to be odd. So let me to take this p as 3. So this means 4 into 3 taking k is equal to 1. This quantity becomes 12. So 12 also have no primitive root. So whenever this number is divisible by the product of the two quantity, effectively, whenever we will have a situation that the number is divisible by product of two quantity and the GCD between those two quantities is 1, the number n will not have a primitive root. Moving forward to the next case, so we'll have the first lemma 1. If p is an odd prime, then there exists a primitive root r of p such that which satisfy this type of the congruence, that r raised to power p minus 1 is not congruent to 1 modulo p square. In my earlier video on the primitive root, we have already discussed that whenever p is an odd prime, there do always exist a primitive root for every prime. So this is what the statement says. If p is an odd prime, then there exists a primitive root r of p. So this means p odd prime, there exists primitive root r of p. So when there exists a primitive root r of p, this means r to the power phi p is congruent to 1 modulo p. This will hold. Now in addition to that, we also want to consider a congruence of this type that is given here now by the equation number 1. So suppose one holds. If one holds, then there is nothing to prove because we wanted to prove for not congruent, which is fine. Then we are done. On the other hand, suppose it holds. So this means r to the power p minus 1 is congruent to 1 modulo p square. Okay. Suppose it holds. In that case, what we need to do is we need to simply replace r by r plus p, and I am just calling this as r dash. We can do this because whenever we talk about the primitive root, we always start searching. Suppose we want to search for a primitive root modulo p. So this means I am going to search the primitive root between 1 to up till p minus 1. Okay. and all the numbers, if the primitive root exists after this quantity, that is p plus 1 and so on, they will be congruent to one of these element which is primitive root in the previous set itself. So this is r plus p because this p is congruent to 0 modulo p, so it remains r. But now let me to prove this theorem, because we wanted to show that for any number this is not going to be congruent to 1 modulo p square, the equation 1 hold. So replace r by r plus p equal to r dash, and this means r dash raised to power p minus 1. So this is what we require, phi p power. So I am just keeping the power as phi p. This is same as r plus p whole to the power p minus 1, and applying binomial theorem here, it is simply x plus y raised to power this. This is congruent to r to the power p minus 1 plus p minus 1 p into r times p minus 2 modulo p square. Because in all the other terms of the binomial expansion, when we open this quantity, we find every term contain p square. Every term will contain p square, and the last term will contain the order p into p minus 1. So these are the only two quantity which are not congruent to 0 modulo p square. And we also know that this quantity is congruent to 1. We have just done from the star. So let me to consider this equation number as 2. So this hold from 2. This hold from 2. And the other quantity, this is plus p minus 1 into p into this. So once I multiply, I get p square r to the power p minus 2 minus p times r to the power p minus 2 modulo p square. Again, this quantity is congruent to 0 modulo p square. So this means I am only left with 1 minus p into r to the power p minus 2 modulo p square. Now if I look at this expression, this is now r dash to the power. So let's me to write this again, r dash to the power p minus 1. This is congruent to 1 minus p into r to the power p minus 2 modulo p square. Now this expression would be congruent to 1 if this quantity turns out to be congruent to 0. But this will not be congruent to 0. Why? Because r is a primitive root of p. And hence the GCD of r and p is 1. And hence p does not divide any power of r to the power p minus 2. Now if p does not divide r to the power p minus 2, this means r to the power p minus 2 is not a multiple of p. If it is not a multiple of p, so we have in this quantity only a single power. We only have a single power of p. Okay, so p square will not divide this whole quantity. That means this whole quantity is not congruent to 1 modulo p square. But our assumption is 2. But from 2, r to the power p minus 1 is congruent to 1 modulo p square. So that contradicts our choice. So this contradicts our choice, and hence this has to be not congruent. This contradicts our choice. This gives us a very nice corollary that if p is an odd prime, then p square has a primitive root. And to be very specifically, what we can say is, for a primitive root r of p, either r itself or r plus p or both. So either r or r plus p or both is a primitive root of p square. This is a primitive root of p square. So this gives us a very wonderful result. We know that every prime has a primitive root, and hence its square will have a primitive root. And if you know that what is the primitive root of that prime, according to that you can find what is the primitive root for p square. So for example, we can look here an example also. We know that 3 is a primitive root of 7. 3 is a primitive root of 7. So this implies 7 square, this is 49. So 3 and so r or r plus p. So r or r plus p. Now here the value for r is equal to 3. So r plus p is 3 plus 7, that is 10. So 3 and 10 are primitive roots of, these are primitive roots of 7 square. Now we prove the lemma 2. Let P be an odd prime and let R be the primitive root of P with the property R raised to power P minus 1 is not congruent to 1 modulo P square. Then for each positive integer K greater than or equal to 2, this congruence also is true. Now to do that, we follow exactly similar arguments as we did in the previous cases, lemma 1 and the other cases. So we want to prove again by induction on K. So for K is equal to 2, just simply substitute the value for K is equal to 2 in the desired congruence. So when we put K is equal to 2, it becomes P to the power 0 into P minus 1, and hence it comes out to be not congruent to, and the result is true. We'll assume the result for K and we will prove for K plus 1. Now to prove for K plus 1, I have started from Euler theorem, and here in the modular condition we start from P to the power K minus 1. And here we note that the GCD, because R is a primitive root of P, so this means P is any power, GCD is 1. And if for P is any power, GCD is 1, by Euler theorem this result will always hold. And this result will always hold, and again we have only opened the power of phi P to the power K, which is this quantity. And then I have written here it as a multiple of A into P to the power K minus 1. Raise both side power to P. We finally get this is still not congruent as following the similar condition. Now these two lemma help us to prove theorem 3, which says that if P is an odd prime and K greater than or equal to 1, that every power of P has a primitive root. In earlier cases we said that prime has the primitive root. So that means 5 has a primitive root, 5 is a prime, 7 has a primitive root, 11 has a primitive root, but their powers is not a guaranteed a prime number. Say for example P square is not a prime number, P3 is not a prime number. But from this theorem we are talking about the composite numbers which are actually written as the prime square. Okay, so something like 7 square. So now it guarantees us that if P is an odd prime, then there exists a primitive root for P to the power K and for all powers K greater than or equal to 1. Let us now prove this case.